we see that there's just an increasing amount of demand for much more sophisticated signal processing on orbit, and we're working hard to satisfy the needs of these ever more complex algorithms.
In this episode of Embedded Insiders, Ken O'Neill, space architect at AMD, joins us to explore the company's advancements in AI for space. He delves into how AMD is enabling onboard processing for satellites and spacecrafts, including the adoption of FPGAs and spaceflight applications. But first, Embedded Computing Design's editor-in-chief Ken Briodagh shares highlights from Computex 2025, providing insights into the top technological innovations unveiled at the event, including advancements in AI and edge computing.
Good afternoon. Welcome to the Embedded Insiders podcast with me, Rich Nass, Ken Briodagh, editor-in-chief of Embedded Computer Design. How you doing, Ken?
I'm doing all right. Mostly recovered from my jet lag, I think.
What do you mean jet lag? It's only a 17-hour flight. How'd you get jet lag?
Hey, we were quick. We did it in 15. But honestly, the jet lag was not that bad coming back from Taiwan. I slept the first 10 or 11 hours of that flight, and that reset me nicely. So
wow,
pretty
that's
good.
Awesome.
Oh, yeah.
I know we're recording, and I shouldn't ask you this, but was that a medicated sleep, or
it was not. That was a naturally occurring exhaustion sleep because Computex was busy this year. We were running. I was out meeting with folks, actually all over Taipei. We did a bunch of home office meetings with some of our friends there, and collected a lot of good stories. Recorded a ton of video. As some of our folks listening will know, and some may not, our YouTube channel has become very active lately. And so we did a bunch of YouTube shorts with some folks talking about some interesting tech from MSI, who everyone knows for their cool laptops, but is also pretty heavily involved in the server space. And they had some really interesting rack announcements. And they also launched a EV electric charging division that they were talking about there. They've got charging stations and a whole software platform for managing both the high power stuff and like at home residential style. So interesting that they're getting into that business. But that's just one of the many cool conversations we had there. It was a really busy show. Really good. Plus, I got to do a little bit of touristy stuff, which is nice.
Okay, before you leave this subject, how do people find those videos?
Go on over to YouTube and go to Embedded Computing Design on YouTube. You can find not just those shorts, but also video interviews and my news segment covering a bunch of different things that I saw at the show from Advantech and a bunch of others. Okay. Advantech was actually interesting. That was their first time back at Computex, despite being headquartered in Taiwan in, I think it was 12 years. They hadn't done a booth there in that long, and they're back now. They also did, as they do, I think every year, a sort of satellite event at their headquarters where they did like some workshops, and I got to go over there and see some roundtables with their CEO KC, who has been threatening to retire for years, but this time might actually mean it.
So that's actually one of the most enjoyable things with Advantech is having the opportunity to sit down with him. He's amazingly forthright and honest when you ask him a question. Usually a CEO, they give you some marketing spin answer, but he answers the questions.
Yeah. Unfortunately, I did not get a chance to sit down with him on this trip. His schedule was too tight. We couldn't make it happen. I'm hoping to do a segment for this podcast with him at some point.
That'd be awesome.
But unfortunately, I wasn't able to sit down with him. But that aside, really good series of events. We did a cool tea party with a bunch of folks at this great little coffee shop, tea shop called it was Wild Kitsune or something Kitsune, a little fox themed thing. It was very cool, very good. They had delicious little fox shaped sugar cookies that I must have eaten about 40 of. that were really, really good. And we talked about AI. You know, the themes of the show was AI, edge, AI, agentic AI was really big, especially considering that so much of this show was hardware focused. You know, it was not, at least from my perception and the folks I was talking to, not a software focused show this year. Almost all of the really interesting AI stories were about growth, implementation, and development of agentic AI in small data models. You know, it was not about large data. It was about, you know, tailored, specifically trained data sets for specific purposes, and having that agentic service-oriented UI paired with it. And I thought, personally, I find that to be a very positive area of development as for AI. So that was refreshing and great for me to see, especially coming off the sort of grandiose language that you hear from a NVIDIA GTC.
Speaking of NVIDIA, was there any discussion about their lower end GPU that they're supposedly doing for folks in China?
Very little. You know, it was out there. It was part of the discussion, but it was still all the high end stuff from NVIDIA. Jensen Huang did a keynote, and the lesson there was very much about agentic and tailored and AI everywhere, big AI, that kind of thing. So they were not in at least messaging or conversation focusing on that, but it was present.
Okay,
Which
excellent.
I thought was interesting. I thought they would, especially in Taiwan, focus pretty heavily on that. But I mean, this is simply opinion. I think that they're focused really heavily still on Blackwell and on making the big data set play happen, and still leaning on opinion. I think it's a misstep. I don't think that's ever going to be the big thing, and I think it's going to be a bit of a boondoggle in a couple of years looking back. But that's just me.
Yeah, unfortunately, some of these talks by people like Jensen Huang specifically, as part of the Magnificent Seven that they call them, they have to be so careful and guarded about what they say because it affects the whole world from a financial perspective. They say the wrong thing or the right thing, and a stock can go up or down, and people lose billions of dollars very quickly.
Yeah, it's interesting. I was able to talk with, and I don't want to say specifically who, but a major manufacturer. There was so much storage there. This was one of the storage companies, and we were talking about manufacturing and the tariffs and things like that, and like the uncertainty in that world. And they were saying, you know, people, which is what we've been saying, people are putting in manufacturing all over the world in order to hedge their bets against what is the US going to do? What are companies like NVIDIA going to do? Because all of this resting on that Magnificent Seven or a tariff thing going into place or whatever is a lot of uncertainty in the marketplace. I heard tell of a company building manufacturing plants on both sides of the US-Mexico border and just shifting the staff from one to the other depending on what the market does on a day-to-day basis, and having mirrored, you know, factories, which I found probably apocryphal, but but interesting.
Interesting. Very good.
Yeah.
Well, I'm glad you had an enjoyable time and you were able to do a little bit of touristy stuff because we don't get to do that too often. So that's great.
Yeah, I had a wonderful time at the night market on my last night there. Ate everything I saw, and managed to gross out Patrick, who was there with me, as I ate whatever there was. And then did a nice museum before I left on my flight. So yeah, a little bit of touristy stuff was nice.
Good. Excellent.
Yeah. Well, I suppose we got to get to the rest of this episode. You got some great interviews coming up out there, folks. So keep on listening. Make sure you subscribe. Make sure you send this to folks you think would benefit from these really interesting discussions. And we'll catch you next time on Embedded Insiders.
Now, here's AMD's space architect, Ken O'Neill.
So I'm the space systems architect at AMD. My name's Ken O'Neill. I've been at AMD for about 3 years at this point, and my background is in the adoption and the use of FPGAs in spaceflight applications, and I've been working in that field for about 25 years at this point. As I said, 3 years recently with AMD, and for more than 20 years prior to that with other organizations.
Awesome. So I kind of just wanted to know how AMD got started in this space, the space of space exploration and satellite operations, and what's
Sure. Yeah, so I can give you a little bit of background info on that. So what we've seen over the years is space as an application area has been growing pretty dramatically. Not just the number of satellites and the number of space probes that have been developed, but also the amount of data processing that needs to be done on board the satellite or on board the spacecraft. And we see this in pretty much every area where spacecraft are deployed. So that can be scientific, astronomical types of applications, or remote sensing, Earth observation types of applications, or in communications, or in precision navigation and timing types of applications. So basically what's happening is sensor resolution is increasing dramatically. So an easy way to kind of visualize that is, if you think about how resolution in digital cameras has improved over the last 20 or 25 years. I remember my first digital camera was pretty much VGA standard, at 640 pixels, and now we're into many tens of megapixels of resolution just for consumer cameras. The same is true for cameras and imaging systems that are used in space. And I like to use imaging as an example because it's very easily understandable by people. But if we think about radar systems, or we think about RF systems, or other types of sensors that measure physical phenomena, the same improvement in resolution and improvement in frame rate takes place in those types of systems as well. So you got this massively growing capability of sensors in space. And what is not growing as quickly is the ability to transmit data down to the ground where it's being consumed. So we find that we're limited in the growth of signal bandwidth between the satellite and the ground. So what does that mean? It means that instead of sending raw data from the satellite down to the ground station, now you have to do more processing of the data on orbit. And that processing can be basic compression of the data, or what we find more and more in modern times is you're not just compressing the data, but you're actually trying to extract information from the data and send the information down to the ground, as opposed to sending just compressed data. And now we're entering into a new era where instead of sending information, we're actually sending decisions. So the abstraction of data has been increasing on the satellite. So we're entering into the era of artificial intelligence and the inferencing of artificial intelligence algorithms in space. So against that background, you have this need for increasing computing capability on board satellites. And the thing is with satellites, they're a low volume application. So it's very, very expensive to develop a custom chip to do that compression or extraction of information from data. So it's an application that's just ready-made for FPGAs. So with an FPGA like ours, you're able to very quickly and relatively cheaply develop new algorithms and new signal processing capabilities using our parts. So that's really how we came to be in space. There was a lot of demand from the developers of space systems for a very flexible approach to signal processing and data processing, and it's just a natural fit to have FPGAs in space payloads.
So, are there any, primary challenges of implementing, FPGAs in the harsh conditions of space?
Mm, yeah, for sure. So, like, I mean, as you said in your question, space is extremely harsh. It's probably the most unforgiving application environment that exists because we have extremes of temperature, we have extreme mechanical considerations due to the rigors of space launch. And then we have radiation in space as well. So, all of those factors present major challenges, not just to FPGAs, but to any electronic system that's being deployed in space. So to kind of drill into each one of those specifically, temperatures are harsh in space. So if you're in Earth orbit, and particularly in low Earth orbit, the satellite can be orbiting the Earth approximately 16 times per day. And during its orbit, it's going to have periods of extreme heating as it's exposed to sunlight, and then it's going to have periods of extreme cooling as it's traveling through the shadow of the Earth. And so you get these not just extremes of temperature, but these extreme temperature cycles happening with very large amplitude and high frequency at 16 times per day. So that's extremely challenging. When we think about exploring distant planets or even going to our own moon, depending on where you land on the planet, you can be subject to very, very cold temperatures, down in the sub minus 100 degrees Celsius, and in some cases even approaching absolute zero. So that presents humongous challenges, not just for the silicon technology, the die of the electronic component itself, but also the packaging technology can be severely stressed by those extremes of temperature. Then launch provides a really harsh acoustic environment where the components are being vibrated at extreme rates, high amplitude vibration at frequencies from 0 hertz all the way up to several kilohertz. That presents a really harsh mechanical environment. And then radiation is the other one. We find there's really two buckets of radiation, two categories of radiation that we worry about. Total dose is the long-term accumulation of radiation effects that is very gradual in space, and it manifests itself in two main ways. First, as a slowing down of the performance of the parts. So when the parts leave Earth, they may be capable of performing at a high rate, and then over time, the effects of radiation cause the parts to slow down. and designers need to comprehend that when they're doing their system designs. And then the other effect of total dose is increasing leakage current. So we can find that current consumption and heat generation gets slowly worse as the components operate in space. The other category of radiation effects is what we call single event effects. So there's the radiation in space takes two forms. Gamma rays, which accumulate as total dose, which I just mentioned. But in addition to that, there's particle radiation. In low Earth orbit, you're going to be subjected to a lot of proton radiation. And the impact of protons is that they can cause upsets in memory elements and in flip-flops. So you get single bit upsets occurring unless you take specific measures to mitigate those single event upsets. As you get further out into space and get beyond the Van Allen belts, you find that the environment has a lot less protons in it, but has a lot more heavy ions. You can think of a heavy ion as being essentially the core, the nuclear core of an atom. And so we find heavy ions that are much more dense, and as their name suggests, they carry a lot more momentum because they're traveling at higher velocities, carrying a lot of kinetic energy. And in addition to that, they're more massive. They have more weight and can cause a lot of damage. They are responsible for single event upsets where flip-flops and memory cells change state, but they can also cause much more severe damage with something we call single event latch-up, where a high current situation can be caused in an integrated circuit, and if left unchecked, that high current situation can actually permanently damage the integrated circuit. So we're very careful to make sure that we have no single event latch-up conditions in our parts.
Mm-hmm. Well, speaking of that, how does AMD ensure that its solutions are radiation hardened or capable of reliable operation in extreme environments like space?
Yeah, so a lot of the techniques to mitigate radiation effects are proprietary, as you can imagine. So I can give a high level view, but cannot get into too many details on that. Let's say it's important to AMD that our parts operate in a variety of environments, and in fact, one of the things that has become more prevalent as we've migrated down the technology curve is, and I say we as the industry, not talking specifically about AMD here, we find that more advanced semiconductor processes have a larger degree of vulnerability to atmospheric neutrons. So maybe 20 years ago, this was not an effect that anybody worried about. But as we've gone to more advanced process nodes, we found that atmospheric neutrons become something that we need to consider. So what's going on there is high up in the atmosphere, as radiation from space interacts with the atmospheric gases high up in the atmosphere, one of the byproducts of those interactions is actually free neutrons, and they travel at high velocity with a fairly high amount of energy, and some of them persist all the way down to ground level. So AMD is a supplier that supplies integrated circuits for ground level systems such as data centers, carrier class telecommunications applications, automotive applications, medical systems. So we do care greatly about protecting our devices and therefore our customers at ground level applications against the effects of atmospheric neutrons. So we have taken certain steps, which again I can't really get into too much detail on what those are. There's a fairly large number of patents filed at each successive technology generation to mitigate the effects of atmospheric neutrons in our devices. And the steps that we've taken to mitigate the effects of atmospheric neutrons actually turn out to pay benefits for when our parts fly at higher altitudes, like beyond the atmosphere and into space. So we've been able to make use of the steps that we've taken. So what are those steps? So there's certain things that we do in the design of the silicon itself, with how the transistors are designed and how they're laid out on the integrated circuit. We also protect our FPGAs and adaptive SoCs with some inbuilt mitigation for single event upsets caused by neutrons or space radiation, using a soft error mitigation technique that involves reading the configuration and repairing it, and any single event upsets that show up as flipped bits in the configuration of the FPGA or adaptive SoC are read back and corrected with a soft error mitigation software that runs on the part. And I think that's probably all I can say about that.
No, that makes sense.
Yeah.
So how do you see your AMD's technology impacting space? Like AMD playing this role of advancing AI for space applications?
Yeah, so there's actually quite a lot that's going on there that I can talk about. So first of all, we see we definitely see AI being adopted in spaceflight applications, but that's not the only vector that's happening. I will talk about AI in a second or two. In the general context of development of instruments and payloads on satellites, we see this increase in payload signal processing capability and payload data processing capability. So that's an organic trend that's been going on for many years, as I mentioned a few minutes ago, and we see our ability to support that growth in complexity with the latest products that we have introduced as space qualified parts. So those parts have an unprecedented amount of digital logic integration capability, more than 1 million flip-flops, for example, and close to 200 megabits of memory, just integrated into a single monolithic adaptive SoC, along with application class processing and real-time processing. So there's that vector that we're pursuing with ever more complex, ever more sophisticated and capable parts to keep pace with the needs of customers who are intending to do signal processing and data processing on orbit. The other vector is the AI vector, and that's a really interesting one, because we're really just beginning to start peeling the onion on what can you do with AI in spaceflight applications. So what I've seen so far is a number of inferencing applications where a specific AI algorithm or a specific AI function is being used to achieve certain things in space. And I'll give you a few examples that we see coming up pretty frequently. So if you think about an Earth imaging satellite, so there's a number of reasons why you might want to be imaging the Earth, for commercial reasons or civilian reasons. At any point in time, about 60% 60 to 65% of the Earth's surface is covered in cloud. And if you're sending a satellite around the Earth, taking photographs or doing imaging of something on the surface of the Earth, 60 to 65% of your images are going to be the tops of clouds and not really not really useful. So what you don't want to do is waste processing bandwidth, downlink bandwidth, storage space on images that turn out to be just not useful. So cloud detection is an AI application that a number of organizations around the world have been working on so that they make better use of the available resources on the satellite, so that they're not wasting time, power, or bandwidth on sending down images that are just not useful. There's a few other applications that are similar to that, in that they're image-based, image classification and detection. One that's kind of interesting as we enter into a new era of planetary exploration and lunar exploration is using AI to identify safe landing sites for planetary landers or lunar landers. So the last thing you want to do is land your spacecraft on the edge of a crater or land it on top of a big boulder or something like that. So we have a limited ability to map safe landing sites from the Earth. So actually deploying AI on landers so that they can scope out safe landing sites as they're actually going through their entry, descent, and landing phase is something that's really important. So that's another AI application. A little bit of a different application that we've actually developed as a reference design with a partner company is in the field of telemetry anomaly detection. So on a large satellite, you may have several thousand telemetry channels, all of which are monitoring the health of the satellite. So you can be collecting information on voltage, current, temperature, magnetic field, mechanical stress and strain from various points through different systems on board the satellite. And that information is very useful for the satellite operator because it can give early warning of an impending failure of a piece of equipment on the satellite. You may detect that, hey, a certain instrument is overheating, and you might want to modify your use of that instrument, maybe duty cycle it more frequently, power it down once in a while, let it cool, and restart it. In extreme cases, it can indicate that a critical system on the satellite is going to fail. And if you're in a constellation satellite or satellite constellation, such as some of the large communications constellations that we've seen being built out over the last decade or so, you're probably going to have orbiting spares. And if a satellite is failing, you want to know about that as soon as possible so that you can move the orbiting spare into the right location to continue to provide communication services to your subscribers without an interruption in supply. Or an interruption in service, rather. Telemetry anomaly detection gives you a way to understand in real time if you're facing any reliability issues on board the satellite. So there's a class of AI algorithms called recurrent neural networks that are very good at detecting changes in trends in a stream of data. So we created a design that uses recurrent neural networks to predict telemetry values over time, and then detect any deviation from the predicted value, which could be indicative of an impending failure in an instrument in the satellite. So we created that reference design. Uses different type of AI relative to the imaging examples that I mentioned earlier. The imaging examples typically use convolutional neural networks. This telemetry anomaly detection system used recurrent neural networks. So, like I said, we're really just starting to peel the onion on the application of AI in space. And every day there's a new idea for, yeah, how can we use AI in space, and how can we do useful things with AI? So it's a pretty exciting field at the moment, and an exciting time to be working with the space community as we provide a reconfigurable and flexible computing platform on which you can integrate AI applications.
So in addition to the telemetry anomaly detection, are there any other current or upcoming missions where AMD's AI or FPGAs technology is being utilized in space that you can share? If not, it's okay.
Yeah, so the key thing there is what can we share? So yes, I can talk in general terms, but cannot get into any of the specifics.
Right.
There's definitely a wide range of space applications in which our parts are designed in and getting ready for launch, and it does span such a wide range of things. Communication systems. We see a lot of communications satellites that are using our FPGAs for managing network traffic, for doing things like beamforming, packet processing, and other forms of signal processing that are commonly used in communications satellites. Remote sensing is a big area for us as well, because in remote sensing, you're acquiring sensor data from a variety of different types of sensors. Can be optical or RF, or measuring other types of physical phenomena. And in each case, there's a certain degree of signal processing that needs to be done. And what we've seen over the last decade, 15 years maybe, is the emergence of a variety of algorithms that require heterogeneous computing platforms to implement them. So what that means is the amount of data processing, the amount of signal processing that needs to be done is expanding quite dramatically. And each algorithm that needs to be implemented in the course of doing that signal processing or data processing fits best onto a specific type of hardware. So you may find that a certain type of algorithm is best served by an array of multiply accumulate blocks. Another type of algorithm might be best served by operating in programmable logic fabric, where you have a lot of flexibility to interconnect things in many different ways. Yet another type of algorithm is best served by an application class processor that's running Linux. So heterogeneous computing requires multiple different types of hardware building blocks to create the computing platform. It's definitely not a one-size-fits-all type of scenario. You need to have many different types of computing resource available to run all these different algorithms. And that has really driven our development and driven our product portfolio, and will continue to drive our product portfolio going forwards. So, I'm trying hard to keep it pretty general here, but we we see that there's just an increasing amount of demand for much more sophisticated signal processing on orbit, and we're working hard to keep pace with those demands and to offer signal processing platforms that have a variety of computing resources on board to satisfy the needs of these ever more complex algorithms.
Mm-hmm. Are there any key lessons that you've learned about applying this cutting edge technology to such a unique and challenging domain that even other environments that are not the same, but also equally as challenging can take from your work or what you guys are doing in the space?
Yeah. So there is a lot of cross fertilization that's
Mhm.
going on. For example, the anomaly detection system I was talking about, it has applications beyond space. So it's relevant for things like aviation applications, industrial control applications, potentially medical applications. So no pun intended, but in space, we don't work in a vacuum. We do literally, but there's cross fertilization between what we do in space and other things that are happening in other application areas. So the cross fertilization works in both directions. So we're happy to contribute to application areas that are not space, and we draw from application areas that are not space. And a good example of where activity is happening in other domains that has applicability to space. A good example would be automotive. So, for example, there's a lot of development of AI technology for automotive applications. I'm thinking primarily of driver assistance systems there. So there's applicability, but it requires adaptation. So, for example, a driver assistance program that may be looking for pedestrians and bicycles in the roadway is not directly applicable to space because we don't have pedestrians and bicyclists on the moon yet. But the whole idea of object detection and object avoidance, that is applicable. That is absolutely something that's needed in planetary landers and planetary rovers. So we do see a lot of carryover from other application areas that we service with other components and other technology that we produce and supply to customers.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.